A very good morning, class 12th. In this video lecture, we will discuss your chapter number 9 of inorganic chemistry, which is coordination compound. So first of all, let us understand what are coordination compounds. So basically, coordination compounds are the substances in which a central atom is surrounded by non-metals or group of atoms which is called ligand, and these ligand could be your anions like fluorine, chlorine, bromine, or the neutral molecules like we can have ammonia and water. As you can see over this diagram, we are having this is your central atom and all these surrounding elements or the group of elements are your ligands. And all these coordination compounds, or you can say the complex compounds, are a type of additional compounds. So here what do we mean by these additional compound? So basically the compounds which contain two or more simple compounds that can be packed in a definite ratio into a crystal lattice are termed as additional compounds. And these additional compounds are of two types. One is your double salt and the other is your coordination. So let us understand these additional compounds in more detail. So both double salt as well as complexes, or you can say coordination compounds, are formed by the combination of two or more stable compounds in stoichiometric ratio. However, they differ in the fact that double salts like carnallite, Mohr salt, potassium dissociates into simple ions completely when dissolved in water. However, your complex ions do not dissociate into their constituents ion completely. As you can see over there, we have this potassium, which is a double salt, and when it is dissolved in water, it gets dissociates completely into its ions. As you can see over this slide, we are having all its constituent ions over there. On the other hand, we have this particular compound, which is your potassium ferrocyanide, and when it is dissolved in water, so it does not dissociates completely into its ions. As you can see over this reaction, we are not getting this Fe2 plus and Cn minus. Okay, we are getting this particular complex. Okay, this particular complex hasn't dissociates completely into its ion. So this is a difference between your double salts and your coordination compounds, where we have seen that your double salts are completely dissociates into its ions when you dissolve them into your water, and whereas your coordination compounds does not dissolve, or you can say dissociates completely into its ions. Okay, so now let us understand ligands. So basically ligands are the molecules or ions which are coordinated to the metal atom or ions. For example, here we are having this particular your coordination compound, which is your potassium ferrocyanide. Here the Cn is your ligand which is donating electrons to the iron. These ligands can be negative ion, positive ion, or a neutral molecules like we can have your H2O and ammonia. And these ligands are basically of three types. One is your monodentate ligands, another is your polydentate, and the third one is ambidentate. So let us discuss them one by one. So here we have the monodentate, or you can say the unidentate ligands. So monodentate ligands are those ligands which are having only one donor atom. Okay, for example, you are having chlorine and we are having this ammonia. So in this ammonia only N is your donating. Okay, this N is your donating element, and over this water molecule we are having only oxygen as the donating element. So that's why they are termed as your monodentate or unidentate ligands. Now we are having the another category, which is your polydentate, or you can say multidentate ligands. So our polydentate, or you can say multidentate ligands, are those ligands which are having two or more donor atoms, or you can say they are having two or more points of attachments. Okay, so here as we are having this particular oxalate as a ligand, so we are having these two oxygens as the donating atoms, and similarly we are having on this particular compound these two nitrogen act as a donating atoms. So all those ligands which will consist two or more than two donor atoms will be termed as your polydentate or your multidentate ligands. So now let us understand this metal-ligand bond. So this bond is formed between your Lewis acid and Lewis base. So here the ligands which we are having are termed as your Lewis bases. And why is it so? Because it donates the electron. Okay, and your central atom, which is your metal atom, okay, which are basically your D block elements, and these are termed your Lewis acids. Why they are termed as your Lewis acids? Because they accept the electrons. Okay, so as you can see over there, what we have, this particular is your coordination compound, and how is it formed? We are having this particular ligand, which is your ammonia. So what is going to do? It will donate these lone pair of electrons to this silver ion. Okay, so this particular silver ion has accepted these lone pair of electrons, and this particular compound, which is your ammonia, has donated the lone pair of electrons. So it has donated, that's why it is termed as your Lewis base, and this particular ion has accepted these lone pair of electrons, that's why it is termed as your Lewis acid. So to understand these metal-ligand bonding, many theories were proposed by different scientists. So let us discuss them one by one. So there was a chemist, Alfred Werner. He was the first person who put forward a theory to explain the formation of your complex compounds. That's why he is also known as the father of coordination chemistry. So let's have a look over the postulates of the Werner theory. So basically the postulates of Werner theories were actually based on the experimental evidences rather than the theoretical aspects. Okay, so although Werner's theory successfully explained the bonding features in coordination compound, but it has some drawbacks. So according to Werner's theory, your coordination compounds consist two type of valencies. One is your primary, which are ionizable in nature, and another is secondary, which are non-ionizable in nature. Okay, so these two postulates were given by your Werner. It was the first theory to understand the coordination compound. It has some drawbacks. Okay, so the first one is it does not explain why only certain elements form coordination compound, and the another one was it does not explain why the bond in coordination compounds have directional properties. Okay, and the third one was it does not explain the color, why these coordination compounds are so colorful, why they exhibit colors. So this theory does not have any explanation for all these queries. So because of all these limitations of your Werner's theory, a new theory of coordination compound was proposed, which was our valence bond theory, and in short we termed it as VBT. And this theory was proposed in 1931, and which basically explains the structure and the magnetic properties of a large number of coordination compounds. So according to our valence bond theory, the central metal atom has the required number of vacant orbitals for accommodation of the electrons donated by the ligands, as we have discussed earlier. The number of vacant orbitals is equal to the coordination number of the metal ion for a particular complex. So here we are having few silent features of VBT theory, and it says the vacant orbitals goes under hybridization to form same number of hybrid orbitals, means as much atomic orbitals will get mixed up to get hybridized, the same number of hybrid orbitals we will be getting. Okay, and the second one is each ligand has at least one orbital containing lone pair of electrons, and the next is vacant hybrid orbitals filled with ligands to form coordination bond. Coordination and this coordinated bond is stronger if the overlapping between the orbitals is greater. So these were few features of the VBT. So although VBT has explained the structure, magnetic properties and the hybridization of coordination compound, but still there were few limitations of this theory. So here we are having few limitations of this theory. So first one, it contains number of assumptions. Okay, so this VBT consists lots of assumptions. And the second one is does not give quantitative interpretation of magnetic data, and does not explain the color exhibited by the coordination compound. As like your Werner theories, it does not explain why the coordination compounds exhibits color, okay, why they are so colorful in nature. And the next one was does not give quantitative interpretation of the thermodynamic or the kinetic stabilities of the coordination compounds, and even does not make exact prediction regarding the tetrahedral and the square planar structures of your 4 coordinated compounds. And the last one was it does not distinguish between the weak and strong ligands. Okay, so these were few limitations of your VBT. So to resolve all these limitations, a new theory was proposed by the scientists, which was our crystal field theory, in short, which is termed as CFT, which has clearly explained why these coordination compounds are so colorful. Okay, so students, that's all for this video lecture, and hope you enjoy this video, and thank you for listening me.